So then, welcome everybody. I right now see only my presentation, so I can't see who's present. But yes, welcome again to this breakout session on digitalization and battery design. And I added also the word control, since I think if we have the right tools to do digitalization in batteries, then we can also, with the proper mathematical tools, develop from that the control tools which are necessary to, for example, to have a good battery management system. Let me first shortly introduce myself. I'm Arno Vlatz from the German Aerospace Center and the Helmholtz Institute Ulm. Here's my my email address. Okay. And what am I? What I'm doing? I'm working at the German Aerospace Center, heading the Department for Computation and Electrochemistry. We are right now up to roughly 35 scientists and PhD students, all working on modeling and simulation, mostly batteries, but also on thermochemical storage, fuel cells, low and high temperature electrolysis, for example. I entered the field of battery, digital design of batteries, actually roughly 12, 13 years ago in 2008, on the request of some big automotive company who said that they would need a tool, a proper tool to evaluate their batteries, or the batteries they want to use in their cars. And they insisted that they wanted to have a microstructural based tool, since this is based on the material properties and not just on some averaged problem. So we developed, at the time I was at Fraunhofer, we developed this model base and the simulation tools for structure function simulations. To be able to do that on this scale, we need a proper base in solid theory. Therefore, a lot of our work is also develop modeling of degradation mechanism. And since modern batteries are often using electrolytes which are not captured by the standard concentrated solution theory, also theory of electrolytes is important for doing this digitalization of the battery design. And we are, of course, also working on lithium conversion and post-lithium systems. Today, I don't want to go into that. So what do we want to do if we do digitalization of batteries? What are the components we need to put, so to say, into models to develop better batteries? What better ever means for you? And I think I will point out that this is different for any different application. So if you want to develop the tools and use the tools properly, we need to have models for each of the components of the battery. So these are electrode materials, anode, cathode, the materials itself. So mostly then are these powders, but also electrolytes are very important. For example, if you want to avoid degradation, you have to have the right additives. If you want to build up a proper SEI, you need the right additives. And of course, also the kind of salts you are using is important. The separator is not very often considered in modeling, but of course it is essential, since it has to fit to the electrodes, and also the porosities of the separator might be important. So of course, all these things are connected. I mean, you cannot choose electrode material and not thinking about the electrolytes and interacting with the electrode. And also the electrode structure is, of course, dependent on what kind of electrode materials you are using, since electrode materials has to be put into powders, has to be put into electrodes, and depending on what kind of materials you are using, the shape of the active particles might be different. You have secondary particles, you have primary particles. And all these together will influence how you fill your electrode, how the formation is proceeding, what kind of power or energy density you might achieve. And again, the electrode structure is coupled with the cell design for a given design space. For pouch cells, this might not be so relevant, since you can stack them very easily. But if you have cylindrical or prismatic cells, then you have to roll them, the winding, and at the point where you have the biggest curvature, this might influence the electrode structure, that might break locally the structure. So you have to take care of that. Also, and of course, the pack design is, of course, strongly influenced what the cell design might be. And for special application, it might not be enough just to concentrate on on prismatic cell or cylindrical cell. You might have special shapes. I mean, if you think of power tool producer, they have all kinds of shapes of tools, and they have always to build their cells within the design space available to them. And it would be good to have there a more agile kind of production to do that. So this will influence safety and lifetime. But of course, safety and lifetime is also related to the electrolyte and the electromaterial which you're using. So these are all these components which we want to have in the computer, lightly spoken, and we have to build models. So let me first say something about modeling and models in the context of batteries, since I think there are different type of models which are in a certain sense, but can be connected in a certain sense, and this might be also relevant for future development in the modeling in general. So let's start from the battery in a very schematic way. From the battery, usually what you easily can get are the discharge curve or the voltage, the discharge curve, how the voltage is developing depending on the state of charge. And you want to put this into a model. So physics-based model have usually typed this kind of partial differential equation on different complexity. With this physical model, you can also calculate discharge curves. But a more simpler, easier way is to build what I call mathematical models, so resistor network models, which are essentially a set of ordinary differential equations. And if you look more abstract, it's really a distribution of relaxation times, which you're including, which you're building up, and you can basically get the same shape of curves. But the purpose, of course, is very different. I will point out the differences, but in a certain sense, also this physics-based models is, if you solve it numerically, nothing else but a mathematical model. Since usually to solve these type of models, you have to introduce a discretization scheme. Discretization scheme will lead to a set of ordinary differential equations, and you are directly back to the to a very complex distribution of relaxation time, but which are intrinsically related to the physical parameter which you are using in your physics-based models. So in some sense, the complexity of many parameters in a distribution of relaxation time approach is encoded in the time-space structure of a partial differential equations on which physics-based models are built upon. And usually the mathematical models in a more developed way will end up in machine learning, artificial intelligence, since what artificial intelligence is adding to the mathematical models are rules and algorithms, how to adaptively adjust the parameters to get a better and better approximation of reality given the set of data. So what is the difference? Mathematical models have usually excellent agreement with experimental data. They're very efficient to implement. They're very flexible. It's the essence of artificial intelligence. Of course, calibration might be complicated and is only useful very close to the test scenario, so to say. Basically, there's no understanding of processes at all. The prediction of new properties which are not already encoded in the given data is excluded. The physics-based models are supposed to give insight in processes and properties. They should allow study of experimentally not accessible processes. That was what we did the first time for microstructural solved models. We think we can give reliable predictions of trends, but we are not always consistent with the experimental data. And the reason is that we have model errors. And I think I usually interpret this as a good thing, since if our model is sensitive to neglecting relevant mechanisms, we can basically see by comparison with experiments that something is missing and we have to improve our models. For mathematical models, with artificial intelligence, you usually get perfect agreement, but you don't know whether this is true in any sense or whether this can be mapped back again to a physics-based model. But of course, also drawbacks of physics-based model, they're usually more complicated to solve. And if you insist on have perfect agreement, you almost always do overfitting. This means you end up with wrong physical parameters due to unavoidable model errors. So here's one example from my group where we use physics-based models to do really design of thick electrodes. This is studying the risk for lithium plating and graphite anodes for really thick graphite anodes bigger than 70 micrometers. for a perforated electrode and for non-perforated electrode, when you see significant trends for plating, which are capturing correctly the experimental situations. So with this type of tool, you can design the perforation strategy, the thickness of the holes you are using for perforating, the distance, and so on. And you can basically give very detailed design criteria for the type of approach optimization you want to reach for the application you want to optimize. So now we come to the question and answer session. And of course, I mean, this approach then is upscaled to cell models and essentially can also bring back, can be further scaled up to stack model or pack model as shown in one of the projects in the previous session. And now we come to the question and answer session. So in this, the organizer of this breakout session wanted to find out what are the goals, challenges, roadblocks, priorities, and strategies for digital design and control from exactly your perspective. So we are interested in finding out what are your priorities. And since we have only a short time, now left 25 minutes left, which is something we have, of course, a multi-criteria optimization. There is there's never one single answer you can give, since all the problems are connected. But we really want to find out what is your first priority in your application you are doing. So therefore, we can only give you the choice of giving one option. And if after the session there are further questions or need to discuss or will contact me in any way, here's my email address. Just drop an email and I will answer. So now I think I can get out of the, I hope I can get out of my presentation.
Okay, right now I will share my screen to show the question and answer. Yeah. Okay.
So I will shortly explain what this are. I will read the answers, I read the questions, I will explain a little bit the answers. We have 5 minutes for each of the questions. If you have seen, the timekeeping is very strict. So we have to be finished in 25 minutes. And I have also to wrap up the whole thing afterwards. So I will make notes. Raul, do you explain again the Mentimeter?
Okay, so it's the same as the other time. Can you hear me and see my screen?
I can hear you.
Yeah, okay, so you just have to go open a new window in the Explorer, Internet Explorer that you are using, or just with the QR with your phone. You can join this menti.com using this code or just the QR. So let's wait some time until everything is on board. Okay. And then I will start with the first question. Okay. So.
Okay. So the first question, which the organizers were thinking of, what are the pain points or the bottlenecks in digitalization, the battery design? Well, computational time might be the most obvious one. Model complexity is certainly an issue. If you have a very complex set of partial differential equations, it's very hard to understand sometimes. On the other side, it also leads to a high number of input parameters. But okay, you're faster than I can explain. So then the necessity of parameterization is also an issue. As again, everything is connected, and therefore it's hard for you probably to choose. Also, right now, parameterization seems to be the most important issue for you. Well, I'm astonished that model accuracy is not so relevant. I usually try to make good, very accurate models. Hardware investment, okay, nowadays hardware is getting cheaper and cheaper, that's true. So high number of input parameters, necessity of cell parameterization. It's true, I mean, this is the same thing. Basically, nearly half of the audience, nearly half of the audience thinks that the parameterization is certainly the biggest problem. Model complexity is difficult sometimes to explain. As I said, model complexity might be a very complicated set of equations, which is difficult to understand. So now things are not changing anymore. So I have to see what I have to do the timekeeping. So everything seems to be stationary right now.
Yes.
Good.
So I think shall we go to the next question?
Yeah, parameterization seems to be the biggest problem or the biggest concern.
Okay.
Let's go to the next question.
Still, if someone has any more questions, you can write it in the chat to Arnulf or to me.
So which are the main expectations from regarding the digitalization and battery design? Optimal design, I mean, you have to design what is optimal for you. Better quality products is certainly an issue. Time to market. If you're really developing a lot of batteries, different type of batteries, this is an issue. Reduce costs. I mean, for any commercial company, this is a very, very important point. The enhancing battery performance is something on reduce cost, and battery performance enhancement is, of course, in contrast to each other very often. So one has to choose or find the optimum. It's not a real choice here. I mean, you really have to optimize both things. As I said, all these questions are multi-criteria optimization problems. So if you go too much in enhancing battery performance, you might have a very expensive battery design, which is sometimes necessary if you have a battery, for example, for space application. You want to really have a battery which is working for many, many years, since you have no way to control it. On the other side, if you have a battery for a e-bike, you can change it relatively often, and it's not too expensive to do it. So battery performance still the first, and better quality products, optimal designs. Consider the good thing that only 5% are saying others. This means we find at least some relevant issues to consider. I'm a little bit surprised that reduced time to market is not is of so low concern. That's an interesting point for me. Just write down notes to market. So again, we seem to be stationary. So battery performance enhancement is the biggest issue, which is probably still relevant if you think of automotive applications. And this is certainly one big bottleneck to be overcome in the near future, actually. Good, so battery performance is the biggest point. So I didn't check when we start. So right now I start to lose my time keeping.
It's okay. I think that we are okay on time. So okay. I just will move to the next question.
Good. So what are you doing to reach your goals using a digital approach in battery design? Of course, there are different strategies which you could choose. I mean, you could just outsource, take a service provider, some company, engineering company, or a research institution like ours. You can hire the right persons. You can go in for a long-term partnership with some specialized company, which is a certain issue. Now I lose the questions. I only see the answers, so I cannot really comment on in-house training. Of course, I mean, you can have somebody in-house, not located in a department, but somebody in each department who knows modeling and simulation. But you can, for big companies, is an issue, also create your own department. So in-house training is certainly important. Specialized companies might also be research companies, research institutions like DLR, Fraunhofer, and so on, and institutions in general. Specialist recruitment is probably the predicament for having in-house training. I mean, it's good to have an outside, somebody hiring from outside, then you don't have to do the training yourself. Okay. So in-house training, partnership. In-house training means, so now I think that we should have probably added a different issue, namely who is doing the in-house training. So is this again from some person inside, or is this again training from outside? So long-term partnership is for a big company, automotive company. You can really do partnership with software companies. I have seen Robert Spotnitz being here. So a person like him is certainly a long-time partner for doing optimization of batteries. Okay, so this, I think, I find it's good that you're really relying on your own competences. So this is a great thing. So having experts or specialists in the company doing simulation and modeling is also something preferable if you want to have contact to outside partners. And this makes the discussion, of course, very much easier to do. Okay, so in-house training seems to be the most preferred one. Also, partnership with specialized company is not much far behind. So these are the two things. So I would say having your own competences and align them with experienced external partners is probably the best strategy to do. Outsourcing could be sometimes problematic, since then you have no control on what you're doing, and you have to always go to an outside partner, which might sometimes make the process difficult. So in-house training together with external partners. Okay. I think we can go to the next question. So now the next two questions actually were chosen by me, and I wanted to find out a little bit about what are you specifically the technical aspects which you want to improve if you apply digital techniques. Again, it's very hard to. I mean, this is now very difficult since it's overlapping. So the pack design, okay, this is. Okay, 3 persons pack design, raw material properties. This would probably mean that you have DFT. I mean, for material developers, this is what you have to do. I mean, there's no choice actually for that. But of course, if you are just applying batteries, then this might not be the most preferable issue. Electrode structures is something, actually, this first automotive company was really interested in electrode structures, not just in the cell design. Here we are really equally distributed. Okay, interesting. Okay, in some sense, what I'm seeing here is that you are aware that you basically need to improve everything, and therefore you basically have to attack the whole, so to say, the whole package, which actually is the wise strategy. Since, as I explained in my introduction, you cannot improve pack design without having a proper cell design, and this is also relying on the electrode structures, and the electrode composition is something. Here, I always find it very difficult, since electrode composition, even for our modeling approach, is sometimes very hard to get parameterization, since the companies building or making electrolytes, they are very, very reluctant in giving any really sensible information for modeling. So this is a very hard point for parameterization, which we had before. Electrode structures is easier to attack. Pack design, yeah, I should have mentioned pack design, of course, then means, of course, thermal management and control is something where BMS here is very much relevant. So here the tools are different from the electrode structures. Okay, here I see basically that you know that you have to do everything at once, which is probably the right answer. Okay. Since nothing is changing anymore, I think we can go to the last question. So what is your main technical focus in digital design? Again, I mean, it's hard to choose. Let me explain the last two ones. I mean, you can increase power density and energy density if you know you want to have a battery which has to last 15 years. If you have very special applications, if you have high, heavy duty appliances, then you know that you have the high load. You have to have the high power, and you just have to change the design to get to increase the lifetime. So there is nothing. I mean, you cannot avoid that the battery is not living 15 years. The SOH. This is the two last questions were actually related to what I said before. namely that once you have the tools to do the design, you can also use the same tools to evaluate how you can use your battery, for example, in second life application. And the last point is the adaptive operating strategy. I had in mind, for example, I mean, this is very special to us. We are, for example, developing tools to follow the state of health of a battery which is living in a satellite, which is still in orbit. And of course, we don't have any information on the internal life. It's in orbit for 15 years now. And we have basically to guess or to use our modeling tools to learn something about the internal state and then to adapt the strategies for operation. And this is what I mean. If over lifetime, basically, the operating strategies are changing, having the right digitalization tools might be what you need to adapt your operating strategy. I guess iPhone is doing it was doing it for some time when they changed the lifetime or the charging, the speed with which you can charge your phone. So here, okay, this is interesting to see that the increase in lifetime in the high load conditions, that this is a very important issue to go for. I mean, this is for special application. I think I also see that this is a very, very crucial point. As I said, power tool producer, they have exactly these problems that you want to use this tool under very hard conditions, and you want to have heavy load, high powers, which you want to apply all the time. And of course, then the increasing the lifetime is a very important issue. So, lifetime. So then the next one is the adaptive operating protocols for special purpose applications. Okay, good. Yeah, then thank you. So Raul, what is the time? Do we still already have?
We have 3-4 more minutes. So I think that there are some questions in the chat. Maybe you can look at it. I received one from SP. What should be the approach role of a mechanical engineer in the battery industry?
I mean, mechanical engineers, I mean, they are the real expert. I mean, we are fighting, for example, in developing the right tools to do mechanical simulations of batteries. I mean, the expansion of the anode graphite, and it's of course getting worse if you use silicon in your anode, and to calculate the stresses under this condition is a very important issue. Here we often were able to use, since the tools were not yet available, to use on one side electrochemical simulations, which gives you the electrochemical state, and then use something like one of the specialized mechanical solvers. I don't want to promote any special company, but you all know the main tools which you use to do mechanical solid mechanics simulation in your application. And then you can basically use if you have the right models, you can usually input the electrochemical state from the electrochemical simulation into the mechanical simulation and calculate from there the expansion of the batteries and the stress. Or if you simulate the extent of plating, you can calculate what is the consequence of plating on the mechanical stress in a cell. But actually, this is right now one of the fields, one of the bottlenecks we see very often, that the coupling between these two things is not yet in the stage which we want to have actually right now. So mechanical engineers is something very important if you calculate also the state of the battery within a pack, since each of the cells is expanding, and you have to control in a pack basically the stress from one cell to the other. Of course, if you go to solid state batteries, stress is the issue which you have to have under control. Electromechanical simulations there are very crucial and very important.